Hello everyone, in this video we'll be solving problem 52 n queens 2. The problem statement is asking us to return distinct solutions where we can place n queens on an n by n chessboard where no two queens can attack each other. In example number 1, where n is given as 4, there are a total of 2 combinations where all of the queens can be placed safely without attacking each other. The problem statement is very straightforward, but the solution is a bit tricky. So now let's switch to whiteboard and discuss how we can solve it. If you're not familiar with the rules of chess, I'll quickly mention the powers that the queen have. Queen has the power to attack anyone in all 4 directions, that is up, down, left and right. And along with that, it can also attack diagonally. So if you are trying to place one more queen on the board, it cannot be on any of the highlighted cells. Instead of solving the entire problem in one go, let's break it down into smaller pieces and try to solve them. When we place a queen on any of the boxes on the chessboard, we can safely assume that we cannot have any more queens in that particular column. The same rule applies to the particular row. And in diagonal, there are two cases, positive and negative. Diagonal moving from the top left to bottom right is considered positive, while if it is going from the top right to bottom left, that will be the negative diagonal. The reason it is important to decide the direction because it will help us come up with a formula to identify if it is safe to place a new queen in the particular cell. One of the challenging part of this problem statement is to calculate the diagonal positions when a queen is placed on a certain cell. This is because we need to figure out all possible combinations. The best approach to use here is backtracking, where we'll try to place the queen in all of the elements in the grid and calculate what all combinations we can build by placing n queens in the entire chessboard to make sure they don't attack each other. And after trying a certain combination, we'll undo that and try a different pair so that we can figure out all possible combinations. For example, we'll start by placing the queen in the first column and block all the spots where we cannot place queens anymore. That is the entire row and column and all of its diagonal spots. And then from that point on, we'll increment or move on to the next column and see which columns or cells are available for us to place the next queen. And continue that for the remaining columns. So from column 1, we'll go to 2 and then to 3. Let's start by placing the queen at the first element on the chessboard, that is 0 and 0. So all of the elements in that row and column are now taken. If you look at the second row, there are only 2 spots available. The one on the second row is already been covered because queen can move diagonal. So there are only 2 combinations we can build from this point on. Let's place the next queen in column number 2, row 3. So now row number 2 and column number 3 is taken along with the diagonal sides. So all of the cells marked in green and yellow are taken now. If you notice, there are no more cells available in column number 3 to place a queen. All have been taken. So we'll move on to column number 4 where there are 2 spots available. So we'll try to place it in either of the 2. But even if we go ahead and do that, the total number of queens that we were able to place are 3, which is less than the expected. So we cannot use this combination. So as part of backtracking, we'll undo the last operation we have done and try to pair it with a different combination. For example, in column number 2, we try to place the queen in row 3. So instead, we'll try to place it in row 4 and see if it makes a difference. And we'll repeat the same cycle for column number 3 and column number 4. Similarly, once we have exhausted all of the combination from column number 2, we'll move back to column number 1 and try a different combination. Instead of placing the queen at the first row, we'll try to place it in row number 2 and then 3 and 4. The time complexity of this approach will be n factorial, as we started with 4 combinations in the first column, and then for the next one it came down to 2, and then for the next one there are 0. So the possible combination keeps on reducing. And the space complexity is O of n. as we need to maintain on the records where we have placed the queens or which all spots are not available. During the traversal, instead of maintaining a grid of n by n, we can use separate collections to record the rows, columns, and the positive diagonal and negative diagonal spots that have already been occupied or that are available. These objects will help us know if we can place a new queen in a particular cell. Maintaining a collection of rows and columns that have already been used is very straightforward. We can use a simple array of length n and set the corresponding index as false once we iterate over that column or row. The challenging part is the positive and the negative diagonal. These will also be an array, but the size will be 8 or 2 raised to n minus 1. Now you must be wondering why the size of this is 8 or 2 raised to n minus 1 and not n. Let me explain with an example. Let's say we are iterating over column number 3. So we can place the queen in 4 spots. And for all of the 4 spots, if we add the total number of cells that it can touch diagonally, it will always be less than or equal to 8. For example, if we place in the queen in any of the row, on the left hand side there are 5 spots where it touches diagonally or can attack diagonally, and on the right hand side there are 3 spots. Hence we are using this formula to calculate the size of the positive and the negative diagonal array. All we need to do is, once we start the iteration while placing the queen in a particular cell, mark the corresponding position in row and column array to 0 or true and its corresponding positive and negative diagonal as well, and increment our pointer. So look at the next column, and before placing the queen in any of the cell in that column, just calculate the corresponding positive and negative diagonal. Make sure they are set to false in the collection. If yes, then place it, or else look for a different combination. Let's walk through the C# code to get a better idea how we can use this approach in implementation. Here is my C# solution. In the main method, I start by checking if the size of n is equal to 0. If yes, then we return 0. And then initializing my columns, the positive diagonal and the negative diagonal variable with the size 2 raised to power n minus 1. And for the number of columns, it's always going to be n. Now I'm calling this backtrack method, which will help me identify where we can place the queens. In the backtrack method, I'm running a for loop on all of the columns, starting with column is equal to 0 all the way to column less than n. Then calculating the positive and negative index. This is to determine if the corresponding spot is already being taken by a different queen. If the corresponding column, the positive and the negative diagonal, either of them are true, then we cannot place the queen in that row column combination. We continue with the next combination without placing the queen. If the conditions are not suffice, then we set the values to true for all of the corresponding indexes and recursively call the backtrack method by incrementing the row. Once the recursive backtrack method is complete, we then undo the operation and reset the values to false. And during the recursion, if row is equals to end, it means we have exhausted all of the iterations. We just increment the count by 1 and return. The variable count is a global variable, so once the backtrack is complete, we return it from the main method. This code, when submitted on LeetCode, beats nearly 98% of the submissions in terms of runtime and 90% in terms of memory. Thank you for watching this video. I hope you were able to understand the explanation. The details to access this source code is available in the description below. Feel free to check that out, and I will see you in the next one. Thank you.